Hey, this is a little walkthrough chapter 4 again. We had this whole section in chapter 3 and chapter 4 that kind of felt like it overlapped, and it's because chapter 3 deals with the ionic bonding and it also touches on covalent bonding, but then chapter 4 really focuses in on covalent bonding and goes into structures and things. So what we did was I kind of took some of the chapter 3 and I actually put it on the chapter 4 notes. So if you felt like there were things that were a little mixed up in some of the chapters, there's a little section, it was a little bit mixed up. All right, so this was just a big reminder of the difference between ionic and covalent right here. So if that's our periodic chart, and I do look like I'm missing my little top corners here. So if this is our periodic chart, you'll notice that I've got this section right here that says ionic. And what that is when you take a metal, and notice that, everything on this side is a metal, right? So if I take a metal, and notice I've got it being blue, and then look over here. Do you see how I've got it going into the non-metal? So if I take a metal and I put it with a non-metal, then it's ionic. And that's that whole charge thing. You always have to charge balance things when you have metals. You have to worry about that kind of stuff. When you do covalent stuff, covalents are ones that have on the same side. You'll notice right in here. So it's when these guys are bonded kind of with themselves. And it's a different kind of bonding. It's because they both have a lot of electrons. They share the electrons. They end up going into different shapes. And they have different properties. So they are very different. We're going to go into making sure you remember how to name things. And since you've been doing this as you go along, I feel like it's going to be coming back to you bit by bit. So just have a reminder over here on the left. The reason this picture is here, again, I'm going to zoom in on this. This is ionic bonding. Lithium's on the left side, fluorine's on the right side. And so this is your fluoride. This is your lithium ion. And so what happens is that the lithium is positive because it's lost an electron. So he did have an electron here, but it got moved over to him. And that's why he became negative. Once you're positive and negative, then you have that attraction between the two of them. And they charge balance each other and they match up and they make an ionic bond. And to show the other version of this is a picture showing those electrons doing that. And it's the 3s electron. We're only showing the outermost electrons in here. So the 3s electron, this one is the one that goes in and it fills that other space that was missing for the fluorine. All right, so we just talked a whole lot about how the differences, anions and cations, those are what you call the negative and positive things. And we talked about how covalents are different because they have an overlap. We use this word overlap. That also comes up in chapter 5 and kind of have a picture right here of the overlap. They end up getting into the space between them, and that's why both atoms, the red and the green, can both claim them as their own. Remember, there's a thing about 8. 8 is super special in this chapter, and in the chapter that follows, the octet rule is very important. We aren't to this part yet, but we will be going in this direction. That is what something that's covalent looks like. That's covalent bonding. They form those shapes, and we have names for them. Up here, this picture right here is what something that's ionic looks like. You end up with just like a big old pile of positive and negatives alternating. You have like this ordered structure, these cubic kind of shapes, forming these things called crystal lattices. So that's what the ionic looks. And so you can see there's a very different way that they look. Okay, so naming. Let's name things well. So there is a flow chart on another page. If you want to use the flow chart, you can definitely use it. The whole section of naming that we start with is we start by naming a metal and a non-metal. There's two kinds of metals on the periodic chart. So if this is our periodic chart right here, don't forget the tall spots. So there's these metals, and those are our straight up regular metals. They're our alkali and alkaline metals. And then we also have this middle section, and that's the transition metals, right? Both of those metals, you use the name of the metal when you name it. So this right here, if we have KCl, you use it and you say, okay, K, potassium, you just use the name. And like right here, K, you just use the name potassium. And here, iron comes first, that's the metal. And you just say iron. Right here, manganese, you just say manganese. So those are completely similar in that way. They also are similar in that the ending that you put on them, if it's another element, it's always "ide." So notice we have a Cl. So here's our Cl. And so that gives us chloride. And then we have an NO3, which gives us nitrate. Now, the reason that this is named differently is because that's a polyatomic ion. So polyatomic ions just get their name. You don't give them an ending. You don't change it up. You just look it up on your chart, and you just give them their name. So this first element, or the first compound, KCl, is potassium chloride. The next one, you just say the metal's name, magnesium, and then the element chloride afterwards. The next example in here, these are with the polyatomic ions. So you just say the name of the metal and the polyatomic ion's name. Again, the name of the metal and the polyatomic ion name. So this is aluminum and then nitrate. So it all carries on the same way for the transition metals, this section in here, except that you also need a Roman numeral and you have to figure it out. And it's because these guys can have extra charge values. So for example, we're going to zoom really close in right here. This is iron 2 chloride because I can't say that my iron is +2 just by looking at it. I have to look at how many chlorines are attached. There are 2. And my chlorines have a -1 charge. So if I have 2 -1 charges, then the chlorine side of the atom is -2, which means that my iron has to be +2 to balance it and be neutral. In contrast, the one below it is iron with 3 chlorines. Again, the chlorines are -1, so with 3 of them, that gives my total as -3. So I have to have a +3 from the iron. So those transition metals, all they need extra is that Roman numeral, but the rest of it is named the same. If it's an element, it ends in IDE. If it's a polyatomic ion, like right here, we name it with just the polyatomic's name. Acids are the ones where people kind of will start getting confused and they are just thrown a little bit by acids. So acids are named differently than what we were talking about above. Acids are named with hydro. This is when they're AQ, and all of the acids we're going to be talking about today are going to be AQ, and in this whole section they're all AQs. So hydro, and then you put the element's name, but you shorten it. So this is this chlorine guy right here, chlor, and it ends with an ic. So this is for when you have a hydrogen and an element. Hydro, chloric. Right here, hydro, sulfuric. Now that's an exception one because you don't shorten the sulfur one, but you almost always shorten all the rest of them. So you want to go back and practice some of these. What might help is just to look up like the strong acid, strong base chart. And there's a whole list of them. It has all their names just to remind yourself and practice how to name these things. And then if you have a polyatomic ion there, like right here, this is a polyatomic ion. You look up its name. If it is an 8, it becomes an ic. This is the part everyone starts getting confused on. So like here's an example of an 8, and this is an example of the 8. And it becomes ic in both cases. And then over here, this is nitrite. This is chlorite. They both end in ite. And so it becomes us and us. Covalent's really, really easy. It's just prefixes. And so you give everything a prefix, including the second element when it has a 1. The only time you don't give a prefix is if the first element has a 1. So this is called nitrogen, but we do say monoxide for the second one. And like this is dinitrogen monoxide. Nitrogen dioxide. So this is nitrogen dioxide. So you just put the prefixes in. Hydrates are not going to be on the test. You can read this. You can learn this. It was used in lab. And hopefully you understood the naming enough at that point. Then we got into Lewis structures, and we were talking about how on the periodic chart, the columns that the elements are in also tell us the number of valence electrons something has. So the noble gases have 8. And then I have a picture over here just to say, if we're talking about something that has, this right here is going to be like a fluorine. So it has 1, 2, 3, 4, 5, 6, 7. It has room for one more, but it's not there. Electrons on this outside. It has room for that one. But if it has 7, then what that means is that we can call those valence electrons, and we use them as dots. So you'll notice right here, that's what we do. We just put the dots around, and if you remember, you're supposed to make sure that you are putting them in little groups. Imagine 4 circles around them, and you pair them singly before you pair them up. Lots of examples in here. You can come back and practice. Notice that if you are charged, you need a bracket and you need a charge. Bracket, charge. The rest of them, no brackets, no charge. That's just for elements. Then we talked about how you can form structures. So I'm going to move on to the second set of notes on this. One second. Here we go. So when we make these structures, hydrogen is probably the best example of something that you could use where you're comparing ionic and covalent. And so what's going on right here is the hydrogen, you'll notice this, you can see he's got an electron up there. It's being transferred to the chlorine, and you can see I've got it represented with like a blue dot. And so the hydrogen has none. Both of them get brackets, and the hydrogen is positive and the chlorine is minus. That's an ionic looking bond. Now over here, this is a covalent looking bond, and the idea is that they both are coming together, and both of those dots are being shared in that line. So the line represents 2 dots, which represents 2 electrons in a bond. Lines only ever represent 2 electrons, not more than 2. So we had some examples here where, like this example right here, that's an example of it sharing. But then like over here is an example of things that are a lattice. Then we talked about how there are certain elements, and they are in this green section right here, this green section right here. They can have 8, and they have to have 8, and they can't have less than 8, and they can't have more than 8. It has to be 8. That is for carbon, nitrogen, oxygen, fluorine, and neon, but neon doesn't really do anything. There's like not many neon compounds. And then we have boron. Boron can do 6. Boron does do some weird bonding. So if you get to that point of chemistry, you may find times when boron does 8, but we're going with 6 in Gen Chem. Beryllium does 4, and hydrogen does 2. So these were our rules for drawing valence structures. There's more than one way to do this. So if you found a way to get to the right Lewis structures and you like the other way better, that's totally fine. Make sure you're just going with the way that works, and you have evidence that it works every time for you, then that's totally fine. You can work it that way. You're going to add up the total number of valence electrons. Remember those columns I showed on the other page. Actually, it was on the other section. It starts at 1 and it goes to 8. Those are your valence electrons. So add the total number of valence electrons. So right here is us adding the number. Carbon has 4, fluorine has 7, and because there's 4 fluorines right there, that gives us 28. Our total valence is 32. Make sure you keep track of that. You have got to have 32 in your answer. Write the least electronegative element as the center. So that's carbon. He's in the middle. Usually that is the first element. Why can't hydrogen ever be in the center, even if it shows up front? Because it can only make one bond. You're going to space the other ones around it evenly, so fluorine is all nicely spaced around there. Make sure you draw the lines from the center. So that gives us 2, 4, 6, 8 electrons. Now you are going to do this key step. Make sure your central atom has 4. This one does. 2, 4, 6, 8. But that's the step everyone always forgets. Make sure everyone else has 8. Do they all look good? All 8? Yep, they're all at 8. So if it comes out the same as 32, then you're great. You're good to go. If it doesn't, then you are going to be moving on and you're going to be learning about how to make if you don't have the right number of electrons, you either put the extras on the middle atom or you make double bonds, triple bonds. And I'm going to move on to... These are the other topics, and then we're going to look at the examples of the Lewis structures. So we had 3 general areas. We had resonance structures right here. And then we had formal charge. And then we had polarity. So resonance structures is when you can write 2 things and they both, like it's got the same elements on the outside and they both look like they are almost the same structure. You can't tell why, you can't tell that the left one is any better of a structure than the right one. It only happens when you have the same element on the outside, the same element on the inside, and you have the option to make a double bond somewhere. So that means that we have something resonance. The big thing on resonance to make sure that you understand that this bond and this bond is somewhere in between what they look like they are. So it's the average length of a bond. Then we have formal charge. So with formal charge, we did a lot of counting with formal charge. Let's take a look over here at the oxygen. So oxygen has 6 is his valence number. We subtract out the dots, which are the valence electrons. You can see he's got 4 valence electrons. And then we have our 2, which is our 2 bonds. So that gives us 0. You keep on moving on down here. These are some examples of things that have a formal charge that aren't 0. So like this structure is not the best structure because everything is not 0. Notice that like oxygen, here's the count for him. He's got 6. He's got 2 lone pairs right here. And he's got 1, 2, 3 bonds. So his formal charge is 1. We represent it with a circle and then we put the charge inside of it. And there's some general rules about formal charge if you want to go back and read it. And then we have polarity, and polarity is when we talked about electronegativity before, we talked about electrons being pulled like in one direction. Well, so for polarity, it's when you have a structure where you have lots of places for bonds, and then let's say like all of the electrons are being pulled out. Well, the bond has polarity in that case, but if it looks like this, the structure does not have polarity because they cancel each other out. This was a big topic we talked about a lot, is canceling each other out. So that picture does not have polarity. However, if instead of that picture, you had something like this, and you had a lone pair in there, and these electrons were here, and they were here, and they were here, well, now you definitely would have polarity because there's no one to balance out like this guy. So that's polarity, and we talked about how you can actually, there's a scale for this, electronegativity scale, and ionic is when it was greater than 1.8. And we were talking about assume polar if you have different elements. So assume that unless it's one of these 2 shapes. If it's the same elements, you assume polar unless it's a square planar or it's linear or it has no lone pairs. So we're going to look at the 2 pictures with the structures. So you should have worked these in lab. Something similar to this, you should have worked these in class. We did these in a certain order. So you'll notice that the electron geometry, we did it in order. So that here's my linear grouping. Here's my trigonal planar. And I left out the other trigonal planar. Here's my 3 tetrahedrals. And then I've got all these trigonal bipyramidals. And then I have some octahedrals. So what I've just put squares around, those are the families, and this is the part that people get thrown on. You need to know this is electron geometry. In contrast, you can also have molecular geometry, which is the better description of the geometry. And so your bond angles, you've got 180. On anything that's linear, it's going to have 180. Trigonal planar, we've got our bond angle here, 120. So I've tried to draw kind of these structures and show how some of these bond angles change. Have some of these examples where we're showing when things have resonance and when they're polar. That these should have been all really straightforward, like basic level ones. If you are uncomfortable with doing these at all, like just pause the video and like cover your hand up and just fill those in. These were like not any strange ones. Once you hit this section right here, you ended up, right here, you ended up having to do, some of them with lone pairs. And you just put them on the central atom when you had more lone pairs. Like right here. This count came out to be 32 before you put the lone pairs on, and your actual count was 36, so you had extra electrons, you put them on there. And then over here, these were the more advanced ones. Just a few little notes, you can be positive. That's why this was put on here. Starting right in here, this example with the O2. So this one had to have a double bond. When you very first do the count with him having a single bond, you end up with 14, not 12. So you don't have enough electrons, and so that means you need a double bond. And then in the next situation, again, you ended up with 26. And so to get it to the 24, you had to have a double bond. Now, in every place that there was resonance, I have drawn it. And so I don't know if you can kind of see the resonance in this structures right here, but it's there. You look over on the right, you're going to see what's going on with these. And you'll notice that I did have this column marked. You'll notice too, I also on the right hand side, I've got all of these written in about the formal charges, so you can really see which ones end up with some formal charge and where it ends up being. You can go back and you can pause it or go back and look at some of these, like this section here, it's got formal charge. This one has some formal charge. It also has resonance, so I definitely would look at these and decide if you think that it looks like the element should be polar or not polar. The reason we don't put this one as polar is because of resonance. That bond is moving around so much it's averaged out. Sometimes that happens and sometimes that doesn't happen with polar things, but the resonance averages out this polarity in this case. And these last ones in yellow are ones where you actually have to change the number of bonds to fix the formal charge. Oops, not that last one. Those three I circled. The only reason that you can do this is because this central element can have more than 8. If it can have more than 8, then you can fix the formal charge situation. Up in here, all of these, C, C, O, C, those all could only have 8, so you can't fix the formal charge situation. I've got longer videos on all this if you want to watch every single detailed step on putting these in. So you can go back and do that. Last but not least, this is unusual. This is a radical. And you'll notice that right here, there was only one electron, not a pair.